Alright, so in this lesson we're going to start looking at vector addition and kind of talk about how we add vectors together and what that actually means and what that kind of looks like. Some of this is probably review. So let's say we have vector r and we say that vector r is the sum of vector a and vector b. So I've drawn vector a and vector b here. Maybe I know their magnitudes and directions and I've drawn them out graphically here. What vector r would be is this vector right here from this point to this point, the tail of a to the tip of b. What this really says is if you do A and B, you could have just done R and gotten to the same place. So a few things to point out about vector R if we looked at this in terms of vector A and B. One thing is if we look at the x components of A and B, I've drawn the x component of A right here, the x component of B right here, and the x component of R is really the sum of the x component of A and the x component of B. Same thing would be true with the y components. If we looked at the y components of a and b, the y component of r is equal to the y component of a plus the y component of b. Now if these were three-dimensional vectors, we could say the z component of r is also equal to the z component of a plus the z component of b if we really wanted to. So what this really means about vector r, if we look at this in terms of unit vector notation, I could call vector r ax I hat plus ay j hat. There's vector a plus vector b, bx I hat plus bx j hat. And so if I rearrange this a little bit, I could say ax plus bx times I hat plus ay plus by times j hat is equal to vector r. Now of course if these were three-dimensional vectors, that have z components and a k hat over here. Now it's worth pointing out that ax plus bx, well, that's the same as rx. Ay plus by, that's the same as ry. This is really saying that vector r is the x component of r I hat plus the y component of r j hat. This really should be nothing new or nothing shocking if you actually think about it for a second of what this actually means. Really working through a vector this way, if we have vectors in unit vector notation, they actually become really easy to add. And the reason why they become really easy to add is you just add them up, combine like terms, and then, well, add up the things in front of the like terms and get your x and y components. The process of component addition that you did in physics is really the exact same thing, just not written out in this format or this fashion. So let's do a quick example problem. Let's say we're given two displacement vectors, and these are three-dimensional vectors. I've thrown a k hat in there just for fun, and we're going to say displacement c is 2a hat, 2 a's minus a b. Well, this means I'm going to do a twice and then do b in the opposite direction. What 2 times a really means is this would be a scalar multiplied by a vector. What that means is you multiply all the components out there. And then the negative b, remember that's the same thing as flip all the signs on the components or flip the direction of b. Now the nice thing about unit vector notation is I could rewrite this as 2 times a, which is 5i hat plus 3j hat minus k hat, minus b, which is 4i hat minus j hat plus 6k hat. So if I plug some stuff in, what I get is I get 2 times 5, 10, minus 4. 2 times 3, 6, minus a negative 3, so plus 3. Plus, well, negative 1 times 2, 2 minus another 6. And what I would end up with is this expression here. Vector c is 6i hat plus 9j hat minus 8k hat. So that'd be vector c in unit vector notation. Now, what if I wanted to know the magnitude of vector c? Now, that's a very fascinating question because if we have a two-dimensional vector, a x and y component, we know we can use Pythagorean's theorem to find that direction. It happens to work out that we can modify Pythagorean's theorem to work with three-dimensional vectors as well. And the way we would modify it is to just add another square term in there. The distance c, or c squared, is equal to cx squared plus cy squared plus zc squared. You can actually prove this is true to yourself if you really want to by drawing out what vector c looks like in three-dimensional space and finding out there are actually two right triangles you could use to define that distance. One of them dealing with the x and y components, which would give you, well, the distance, what we would think of as the normal radius, the hypotenuse of that right triangle, and you have that hypotenuse plus the z component as your second right triangle. So if we plug in that number and work out the math, we end up with the magnitude of c is 13.45, whatever units this is. Now, the second question we could ask is what direction does c go? That's a little bit more complicated, and the reason why that's a little bit more complicated is we need to know more. We have enough information here, but we would actually need to do two separate calculations. Usually, if we're trying to define it in terms of your normal square Cartesian coordinate system, you would probably want to find the angle away from the x-axis, so one angle, and then an angle away from the xy plane would be the way I would normally think of it. There are other ways you can define those angles. Those would be the two standard ways to define the angles. There are also other ways to define three-dimensional vectors that don't deal with an x direction, a y direction, and a z direction. The advantage to x, y, and z is that it's a, up and down, right and left, forward and back, those three directions. But there are other ways to think of spatial directions which are a little bit different depending upon the situation you're dealing with. Something like a spherical coordinate system may be very helpful, particularly if you're dealing with a system of spheres. Think of finding your location on the surface of the Earth. You're ultimately dealing with a spherical coordinate system. So let's do a quick example problem here, and this may not look quick, but say you've been selected to participate in a reality TV show, and the players in this show have been randomly separated into two teams. So you are with your team, and there's another team out there. And the challenge that each team has been given is to locate a buried treasure chest which contains $10 million for each member of your team. There's only one treasure chest, so the team that arrives at that treasure chest first wins and gets to keep all the money that's in the chest. If your team does not arrive first, you lose and you get no money. Each team has been given a compass, a 100-meter long tape measure, and a set of 4 directions which lead you to the treasure chest. The direction are 125 meters at 32 degrees east of north, 75 meters at due south, 68 meters at 66 degrees south of west, and 65 meters at 10 degrees north of west. So not only have they given you these directions, but 3 out of these 4 directions are not really helpful in a compass anyway because of the way a compass measures direction. The opposing team immediately starts to begin to work to follow the directions exactly as specified listed. Your team has decided to use vector addition to add the forward vectors together and come up with the displacement vector will lead your team directly to the treasure chest without going through all 4 paths. Note in the instructions, it doesn't say that you have to do all 4 of these. It just says you have to reach the treasure chest first, right? And so your team's assuming that you're going to have to walk something less than, well, what is that, 200, another 120, something less than 320 meters if you walk right to the treasure chest, and you only need to find one direction. So you want to find this resultant vector so you can actually do this. So here are the 4 vectors written out: 125 meters at 32 degrees east of north, 75 meters due south, 68 meters at 66 degrees south of west, and then your 65 meters at 10 degrees north of west. And so you're going to try to find the components of all the vectors, the x and y components. And I'm going to define x as the east-west direction, positive x being to the east, and y as the north-south direction, positive y being to the north. And so if you draw out this vector first, 32 degrees east of north, really what happens is that you have a triangle that looks like this, and this angle is the 32 degrees, so your x component will be the opposite side, your y component will be the adjacent side. And so that's how I get 125 sine of 32 degrees, 125 cosine of 32 degrees. B is the easiest. 0 meters, negative 75, due south would be negative. At south of west, well, west is the negative direction. And again, if you do south of west, what you end up with is a triangle that looks like this, where this is your 66 degree angle. And so x component then becomes cosine and y component becomes sine. I would encourage you, if you're confused about how you're getting sine and cosine, draw the triangle and figure it out. It doesn't take that much work. Again, west, south, and then the last one, north of west, there's west, there's north. This should be dy, excuse me. So what I would need to do to find the resultant vector is take all the x components, and I've got them all here. I've actually calculated them out. I've got all the y components here, and find the resultant by adding the vectors together. So you end up with negative 25.43 meters in the x direction and negative 19.83 meters in the y direction. So you're going to have to move 25.43 meters to the west and 19.83 meters to the south. So already if you did that, 25.43 meters west and 19.83 meters south, you're probably going to be going a lot faster than the team that's going to go 4 different legs that are all longer than 25 meters. The next step is to resolve the vector. Find the actual magnitude in the direction. And so here's what this vector looks like. 25.43 meters west, that's what the negative sign says, 19.83 meters south. So we want to find that distance. That's easy enough to do, Pythagorean's theorem. 32.25 meters. That's not very far. And then to figure out the angle, we want to figure out what is this direction. How far south of west are we going to go? So opposite over adjacent. Notice the negative signs also happen to nicely cancel out. And so I get that I have to go 37.9 degrees south of west. Okay, I was just saying some odd things in here, but I guess that's not the case. So the easier way to do this would be to go 32.25 meters at 37.9 degrees south of west, and you would find the treasure chest. That's probably going to be far faster than following all 4 directions as written. Now, of course, we're assuming your team has access to a calculator to do some of these calculations. It'd be kind of hard without a calculator to really do this problem. So that's kind of a quick overview of vector addition and how to use kind of unit vector notation in vector addition, as well as resolving a vector and actually using components to add vectors.